Picture this, a world wrapped in darkness. No forests, no oceans teeming with fish, no birds singing at dawn. Just rock, water, and fire. The Earth, 4.5 billion years ago, was a molten hell, a cauldron of volcanic fury, bombarded relentlessly by asteroids the size of mountains. The sky glowed orange with the heat of impact after impact. There was no oxygen to breathe, no soil to walk upon, no life to observe. And yet, somewhere in that chaos, something extraordinary happened. Something so improbable, so delicate, so utterly miraculous, that it changed the course of this planet forever. In the midst of all that violence and turmoil, the very first spark of life ignited. A single molecule, perhaps no larger than a speck of dust, began to do something that had never been done before. It copied itself. That moment, that singular fragile moment, set in motion a chain of events that would eventually lead to you. Yes, you. Sitting there, watching this, breathing oxygen produced by ancient bacteria, built from the same carbon atoms that once floated in the hearts of dying stars. You are the product of nearly 4 billion years of survival, adaptation, mutation, and sheer blind luck. But how did it all begin? How did lifeless chemistry transform into living biology? How did simple molecules become cells? How did those cells become creatures that could swim, crawl, fly, think, and wonder about their own existence? These are not just scientific questions, they are the deepest mysteries of our existence. They ask us to look back across an abyss of time so vast that it dwarfs human history into insignificance. I, David Attenborough, has spent a lifetime exploring the natural world, bringing us face to face with its wonders and its fragility. But even he, with all his travels across continents and oceans, has rarely ventured as far back as we're about to go. Because this journey doesn't take us to the Amazon rainforest or the African savanna. It takes us to the very edge of existence itself, to the primordial soup, the deep sea vents, the clay surfaces and tidal pools where the impossible became possible. In this video, we're going to unravel one of the greatest stories ever told. Not a myth, not a legend, but a real, evidence-based account of how life began on Earth. We'll explore the leading scientific theories, the breathtaking discoveries, and the unanswered questions that still haunt researchers today. We'll meet the molecules that started it all, the environments that cradled them, and the evolutionary leaps that turned single cells into the magnificent diversity of life we see around us. And we'll do it in the voice of the man who has made the natural world come alive for millions. Because if anyone can take us on a journey from the fiery birth of our planet to the emergence of consciousness, it's him. His words have painted the savannas, the oceans, the polar ice caps. Now, let them paint the origin of everything. This isn't just science. This is poetry written in DNA. This is the most epic adventure story in the history of the universe. And it begins not with a bang, but with a whisper, a chemical whisper in the dark, 4 billion years ago. So settle in, open your mind, and prepare to travel back to a time when Earth was young, restless, and on the verge of its greatest transformation. Because the origin of life isn't just about where we came from. It's about who we are, and perhaps if we listen closely enough, it might even tell us where we're going. To understand how life began on Earth, we must first understand how Earth itself came to be. And that story begins not here, not even in our solar system as we know it today, but in the cold, dark expanse of interstellar space approximately 4.5 billion years ago. Imagine a vast cloud of gas and dust stretching across light years of emptiness. This wasn't just any cloud. It was the remnant of ancient stars that had lived, burned brilliantly, and died catastrophically. When massive stars reach the end of their lives, they don't simply fade away, they explode in supernovae, scattering their enriched guts across the cosmos. Carbon, oxygen, nitrogen, iron, gold, all the elements heavier than hydrogen and helium were forged in the nuclear furnaces of these stellar giants, and then flung into space. Our solar nebula, as astronomers call it, was one such cloud. It floated in the Milky Way's spiral arm, unremarkable among countless others. But something happened. Perhaps a nearby supernova sent a shockwave rippling through space. Perhaps the gravitational tug of a passing star disturbed its equilibrium. Whatever the trigger, this cloud began to collapse. Gravity is patient but relentless. As the cloud contracted, it began to spin, slowly at first, then faster, like a figure skater pulling in their arms. The center grew denser and hotter. Particles collided, stuck together, collided again. What was once a diffuse mist became a swirling disk of material, and at its heart, pressure and temperature climbed until something remarkable occurred. Nuclear fusion ignited. Our sun was born. But the sun didn't consume everything. In the disk surrounding it, a violent ballet of creation and destruction was underway. Dust grains, no larger than particles of smoke, began to stick together through static electricity. These grew into pebbles, then boulders, then planetesimals, rocky bodies kilometers across. And these, driven by gravity's inexorable pull, smashed into one another with tremendous force. Most collisions were destructive, shattering both bodies into fragments. But some were just right, slow enough, angled perfectly, so that instead of exploding, they merged. Gradually, over millions of years, these planetary embryos swept up more and more material from their orbital neighborhoods. The inner solar system, closer to the sun where it was too hot for ice to survive, saw the formation of rocky worlds. The outer regions, cold and distant, allowed ice to condense, leading to the formation of gas and ice giants. Earth was one of these rocky worlds, forming in what astronomers now call the Goldilocks zone, not too close to the sun to be scorched like Mercury, not too far to be frozen like Mars eventually became. But in these early days, Earth was nothing like the blue marble we know today. Picture a world still forming, still in the throes of violent birth. Planetesimals continued to rain down from space, each impact releasing energy equivalent to millions of nuclear bombs. The surface was molten, an ocean of liquid rock, glowing red and orange beneath a poisonous atmosphere of carbon dioxide, nitrogen, and water vapor. There was no solid ground to stand on, no ocean to swim in, no sky to gaze upon, just heat, pressure, and chaos. The young Earth was also spinning much faster than it does today. A day lasted perhaps only 5 or 6 hours. The planet was a fiery sphere, barely distinguishable from the hell we might imagine in our darkest nightmares. And yet, even in this violence, the stage was being set for something extraordinary. You see, those impacts weren't just destructive, they were also constructive in a very real sense. Each asteroid, each comet that crashed into Earth brought with it new material, iron, nickel, silicates, and crucially, volatile compounds. Water, locked in minerals or frozen as ice in the outer solar system, was delivered to our planet through these cosmic bombardments. Carbon compounds, the building blocks of organic chemistry, hitched rides on these ancient travelers. Scientists estimate that in Earth's first 100 million years, it grew from a small planetary embryo to roughly its current size, accumulating mass through countless collisions. The largest of these impacts would shape our planet's destiny in ways no one could have predicted at the time. But even as Earth grew, it faced a fundamental problem. The intense heat from formation, from gravitational compression, and radioactive decay of elements in its interior meant that everything was mixed together. Heavy elements like iron sank toward the center, while lighter materials floated toward the surface. This process, called differentiation, was crucial. It gave Earth its layered structure, an iron-nickel core, a rocky mantle, and eventually a thin crust. The core's formation had another critical consequence. As liquid iron churned in Earth's interior, it began to generate a magnetic field, a protective shield that would later prove essential for life. This field deflects much of the solar wind, the stream of charged particles constantly streaming from the sun. Without it, these particles would strip away our atmosphere as they did on Mars, leaving the surface exposed to deadly radiation. But we're getting ahead of ourselves. In these early days, Earth had no permanent crust, no oceans, no atmosphere worth speaking of, at least not one that would last. The planet was still too hot, still too violent, still too unstable. Any water that fell as rain immediately boiled back into vapor. Any crust that tried to form was quickly remelted by fresh impacts or volcanic activity. This period, stretching from about 4.5 to 4 billion years ago, is called the Hadean Eon, named after Hades, the Greek underworld. It's an apt name. This was Earth's infancy, and like many births, it was messy, painful, and transformative. Yet in all this chaos, in all this seemingly random violence, the fundamental ingredients for life were being assembled. The right elements were present. The right distance from the sun was maintained. The right size large enough to hold onto an atmosphere, small enough not to become a gas giant was achieved. And most importantly, time was on Earth's side. Because what happens next, what transforms this hellish ball of molten rock into a world capable of nurturing life, requires one more cataclysmic event. An impact so enormous, so devastating, that it nearly tore the planet apart. And paradoxically, it may have been exactly what Earth needed. The solar system's early days were chaotic, with planetary bodies still jostling for position, their orbits not yet settled into the stable configuration we observe today. Collisions were not uncommon, but the impact Earth was about to experience would be unlike anything before or since. Somewhere in the inner solar system, another planetary embryo had formed. It was roughly the size of Mars, massive enough to have differentiated into a core and mantle, old enough to have a name in modern science. Theia, after the Greek Titaness who gave birth to the Moon. Theia's orbit was unstable, chaotic, and ultimately doomed to intersect with Earth's. The two worlds had been following similar paths around the young Sun, but gravitational perturbations from Jupiter and other growing planets nudged them closer and closer. It was only a matter of time, and then, approximately 4.5 billion years ago, it happened. The collision was not head-on, which would have obliterated both worlds. Instead, Theia struck Earth at an angle, a glancing blow that was nonetheless catastrophic beyond imagination. The impact released energy equivalent to billions of nuclear weapons, detonating simultaneously. Theia's core merged with Earth's, adding to our planet's mass and iron content. But much of both planets' mantles, rocky material from just beneath the surface, was vaporized and thrown into space. This debris, a ring of molten rock and vaporized minerals, orbited the newly enlarged Earth. Over time, perhaps only a few hundred years, gravity pulled this material together, forming a new body, our Moon. This impact, called the Giant Impact or Theia Impact, had profound consequences for Earth's ability to support life. But to understand why, we need to look at what happened next, as our battered planet began its long, slow journey toward becoming a habitable world. The Moon's formation stabilized Earth's rotation, giving us regular seasons and a more predictable climate. But in those immediate aftermath days, nothing was predictable, nothing was stable. Earth had been struck with such force that its entire surface was molten once again. Any progress toward cooling, toward forming a crust, toward creating an environment less hostile to chemistry and eventually biology had been reset. And yet in the cosmos, destruction and creation are two sides of the same coin. This impact, violent as it was, may have been necessary. It gave Earth the right spin rate, the right tilt, the right companion in the Moon. It mixed materials that might otherwise have remained separate. It set our planet on a path that, billions of years later, would lead to forests and oceans, to creatures great and small, and eventually to beings capable of looking up at that very Moon, and wondering how it all began. But that's a story for later chapters. First, Earth had to cool, it had to form oceans. It had to create an atmosphere that could be more than just a temporary shroud of steam. And all of this would take time, hundreds of millions of years of continued bombardment, volcanism, and gradual patient cooling. The stage was being set, the ingredients were being mixed. And in the depths of this hellish world, something impossible was preparing to happen. In the immediate aftermath of the Theia impact, Earth was barely recognizable as a planet at all. It was more akin to a drop of molten metal and rock, slowly spinning in space, surrounded by a disk of debris that would become the Moon. The surface glowed with the heat of the collision, temperatures soared to thousands of degrees. If you could somehow stand at a safe distance and observe, you would see not a world, but a luminous sphere of magma, occasionally punctuated by vast plumes of vaporized rock erupting into space. This was Earth's second infancy. The planet had essentially been reset, its surface completely melted, any progress toward habitability wiped away. But from this destruction came opportunity. The Moon coalesced quickly, astronomically speaking. Within perhaps 1,000 years, the debris ring had gathered into a single body, much closer to Earth than it is today. So close that it appeared perhaps 15 times larger in the sky than we see it. Now, the tidal forces between Earth and Moon were immense, causing both bodies to bulge toward each other. Earth's magma ocean developed massive tidal waves of liquid rock, rising and falling by hundreds of meters as the Moon passed overhead. These tidal interactions had a profound effect. They slowed Earth's rotation. Remember, our planet was spinning far faster than it does now, and gradually pushed the Moon away. Even today, the Moon recedes from Earth by about 3.8 centimeters per year, a process that's been ongoing since its formation. But let's return to Earth's surface. As the planet slowly began to cool, the first thin crust started to form dark, basaltic rock solidifying atop the magma ocean. This crust was fragile, constantly broken and reformed by convection currents in the molten layer below. Imagine a skin forming on cooling soup, only to be broken and pulled back down as hotter material rises from beneath. This wasn't a stable surface by any means. Volcanic activity was ubiquitous and intense. Massive calderas opened across the planet, spewing lava and gas into the atmosphere. The sky, if you could call it that, was a churning mass of dark clouds, thick with carbon dioxide, water vapor, sulfur compounds, and nitrogen. Lightning crackled through these clouds almost constantly, energized by the volcanic eruptions and the temperature differentials in the atmosphere. There was no oxygen. This is crucial to understand. The Earth's early atmosphere was what we call reducing rather than oxidizing. It contained hydrogen, methane, ammonia, carbon dioxide, nitrogen, and water vapor, but essentially no free oxygen. Any oxygen that did appear through the breakdown of water molecules by ultraviolet radiation from the sun was quickly consumed by reactions with iron and other minerals. This reducing atmosphere, paradoxically, may have been essential for life's origin. Organic molecules, the carbon-based compounds that form the basis of life, are more easily created and more stable in such an environment. In our current oxygen-rich atmosphere, many of these precursor molecules would be quickly oxidized and destroyed. As hundreds of millions of years passed, Earth gradually cooled. The bombardment from space continued, but with decreasing intensity as the solar system's debris was swept up by growing planets or flung into the outer reaches by Jupiter's immense gravity. Each impact still released tremendous energy, enough to locally remelt the surface, but the time between major impacts was growing. Around 4.4 billion years ago, just 150 million years after Earth's formation, something remarkable happened. The planet had cooled enough for water to begin condensing from the atmosphere. The first rains fell. Try to imagine it. For millions of years, water had existed only as vapor, trapped in the hellish atmosphere, unable to condense because the surface was too hot. But now, finally, the temperature dropped below water's boiling point. Clouds formed, not wispy cirrus or fluffy cumulus, but massive storm systems that dwarfed any hurricane we see today. and they released their burden. Rain fell in torrents that lasted not days or weeks, but possibly thousands of years. It fell on rocks so hot that it immediately boiled back into steam, but gradually, imperceptibly, the surface continued to cool. Eventually puddles formed, then pools, then lakes, and finally oceans. These first oceans were not like ours. They were hot, perhaps 80 or 90 degrees Celsius, though this is debated, and acidic, saturated with dissolved carbon dioxide from the atmosphere. The ocean floor was volcanically active, with new crust forming constantly along spreading ridges, just as it does today at mid-ocean ridges. But the intensity was far greater. Underwater volcanoes, called seamounts, were everywhere, pumping heat and minerals into the water. The formation of oceans was a turning point. Water is an extraordinary solvent, capable of dissolving an immense variety of substances. As rain fell and rivers formed, they eroded rocks, carrying minerals into the growing seas. The oceans became a chemical soup, rich in dissolved ions, sodium, chloride, calcium, magnesium, iron, phosphorus, and countless others. These minerals were crucial. Life, as we'll see in the next chapter, is built from specific elements, and those elements needed to be concentrated in the right places for chemistry to work its magic. The oceans provided that concentration. But even as oceans formed, Earth's surface remained violent. The period from about 4.1 to 3.8 billion years ago is called the Late Heavy Bombardment, a time when the inner solar system experienced a renewed surge of impacts. The prevailing theory is that Jupiter and Saturn, still migrating in their orbits, reached an orbital resonance that flung countless asteroids and comets into the inner planets. For Earth, this meant catastrophe after catastrophe. Some impacts were large enough to vaporize portions of the newly formed oceans, sending steam back into the atmosphere and heating the surface once again. The largest impacts may have sterilized the entire surface, destroying any complex chemistry or proto-life that might have been developing. This has led to a fascinating question: when did life actually begin on Earth? If it arose before the late heavy bombardment, could it have survived these impacts? Or did life have to wait until after this period, beginning only 3.8 billion years ago when the bombardment subsided? We don't know for certain, but evidence suggests that life may be older than we think. Tiny zircon crystals, among the oldest minerals on Earth, show chemical signatures suggesting that liquid water existed as early as 4.4 billion years ago. And where there's liquid water, chemistry becomes interesting. But let's talk about the volcanism in more detail, because it played a crucial role in setting the stage for life. Volcanoes do more than just spew lava. They're geological factories, releasing gases from deep within the planet. In Earth's early days, volcanic outgassing was the primary source of atmospheric gases. Each eruption sent plumes of water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, nitrogen, and trace amounts of other gases into the air. Over millions of years, this outgassing built up Earth's atmosphere and contributed to the oceans. It also created a greenhouse effect. Carbon dioxide trapped heat from the sun, preventing Earth from freezing solid despite the young sun being about 30% dimmer than it is today. This is known as the faint young sun paradox, and it's one of the many delicate balances that allowed Earth to remain habitable. The volcanic activity also created something else: hydrothermal vents. These are fissures in the ocean floor where seawater seeps down into hot rock, gets superheated, and then jets back up, laden with minerals dissolved from the rocks below. We see these today as black smokers and white smokers, depending on the minerals they carry. They're oases of chemical energy in the deep ocean, and as we'll explore in the next chapter, they may have been crucial to life's origin. Around these vents, temperature gradients exist. Scalding hot water meets cold ocean water, creating zones where different chemical reactions can occur. Minerals precipitate out, forming chimney-like structures. Crucially, these vents create natural chemical gradients, differences in pH and redox potential that can drive reactions, just as a battery uses chemical differences to push electrons through a circuit. But we're still in the Hadean Eon, still in Earth's violent childhood. The surface, though cooling, was dominated by volcanism, impact craters, and newly forming oceans. The sky was dark, the sun frequently obscured by clouds and volcanic ash. The moon loomed large and close, raising massive tides that surged across shallow seas. There was no life yet, or if there was, it existed only as the simplest of chemical systems, barely distinguishable from non-living processes. The continents, as we think of them, didn't exist. Any crust that formed was thin, basaltic, easily recycled back into the mantle by the vigorous convection occurring below. Yet even in this hellscape, the conditions were becoming right. The temperature was moderating. The oceans provided a vast laboratory for chemistry. Energy sources were abundant: volcanic heat, lightning, ultraviolet radiation from the sun, unfiltered by any ozone layer, which wouldn't exist until life created oxygen, and the chemical gradients. Around hydrothermal vents, all the pieces were nearly in place. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, the 6 elements that make up 99% of all living matter, were present and available. Water, the universal solvent, filled the oceans and cycles through the atmosphere. Energy poured in from multiple sources. Time stretched ahead, hundreds of millions of years for experiments to run, for unlikely events to occur. Earth was transforming from a hellish molten sphere into something more complex, more interesting, more poised on the edge of an incredible transition. The volcanic fires still burned, the impact still came, but less frequently now. The stage was set, the actors were assembled, and the greatest drama in the history of our planet was about to begin. All that was needed was for chemistry to cross a threshold, to organize itself in new ways, to begin a process that, once started, would prove nearly impossible to stop. All that was needed was for molecules to start doing something they'd never done before, making copies of themselves. But to understand how that happened, we need to zoom in from the scale of planets and oceans, down to the molecular level, where the real magic was about to unfold. As Earth entered its 2nd billion years of existence, the character of our planet was fundamentally changing. The Hadean Eon, that hellish period of molten surfaces and relentless bombardment, was giving way to the Archean Eon, ancient, yes, but recognizably more planet-like, with stable oceans, a cooling crust, and the first hints of continental land masses. The oceans had now been established for hundreds of millions of years, and they were doing what oceans do best: mixing, circulating, and concentrating chemicals. The water cycle was in full swing. Rain fell on land, what little of it existed, and rivers carried dissolved minerals back to the sea. Evaporation returned water to the atmosphere, leaving minerals behind. This endless cycling acted like a vast chemical filter, moving elements around, concentrating them in certain locations, creating the conditions for complexity to emerge. Let's talk about those oceans in more detail, because they were quite different from today's seas. As mentioned, they were warmer, perhaps with temperatures ranging from a comfortable 25 degrees Celsius in some regions to a scorching 90 degrees or more near volcanic zones. They were also more acidic, with a pH possibly between 5 and 6 compared to today's 8.1. This acidity came from dissolved carbon dioxide, forming carbonic acid, the same substance that gives soda water its tang. But perhaps most crucially, these ancient oceans were rich in dissolved iron. Today's oceans contain very little free iron because it reacts with oxygen to form rust, which precipitates out. But the Archean oceans had no oxygen, so iron remained dissolved, giving the water a greenish hue. This iron would later prove crucial, both for life's chemistry and for leaving us evidence of early life in the form of banded iron formations. The ocean floor was a dynamic place, more active than today's. Plate tectonics, the process by which Earth's crust breaks into pieces that move about, colliding and spreading, was likely already underway, though perhaps in a more vigorous form than we see now. The planet's interior was hotter. so convection in the mantle was more vigorous, driving faster spreading rates at mid-ocean ridges. These spreading zones, where new ocean crust formed, were lined with hydrothermal vents. As I mentioned earlier, these are cracks in the seafloor where cold seawater seeps down, gets heated by the magma below, reacts with the rocks, and then jets back up laden with dissolved minerals and gases. Modern vent systems support entire ecosystems based not on sunlight but on chemosynthesis, bacteria that extract energy from the chemical gradients around the vents. But 4 billion years ago, there were no bacteria, no ecosystems, just chemistry, yet it was chemistry of a very special kind. Consider what's happening at a hydrothermal vent. Cold ocean water, slightly acidic and rich in dissolved carbon dioxide, seeps down through cracks. It encounters hot rock, often basaltic, rich in iron and magnesium. The water heats up to 200, 300, even 400 degrees Celsius, but doesn't boil because it's under immense pressure. Chemical reactions occur. Minerals dissolve. The water becomes alkaline as it reacts with the rock. Then it rises back up through the vent, meeting cold, acidic ocean water. This creates a chemical battery of sorts. On one side of the vent structure, you have hot, alkaline, mineral-rich water. On the other side, cold, acidic ocean water. Between them, a thin barrier of mineral precipitates, often iron sulfides or other metal compounds. Across this barrier, there's a pH gradient, a redox gradient, a temperature gradient. These gradients represent chemical potential energy, like water behind a dam, waiting to be tapped. Here's where it gets interesting. In the 1980s and 90s, scientists discovered a particular type of hydrothermal vent called alkaline vents, or lost city-type vents, after the lost city hydrothermal field in the mid-Atlantic. These vents are cooler than black smokers, around 40 to 90 degrees Celsius, and they form tall, white carbonate structures. The chemistry at these vents is eerily similar to some of the chemistry occurring inside living cells. Inside every cell in your body, energy is managed by structures called mitochondria. These tiny organelles pump protons across a membrane, creating a gradient, and then use that gradient to drive the production of ATP, the energy currency of life. The similarity to what happens at alkaline vents is striking. Could life have begun in a place where natural gradients already existed, gradients that proto-life could eventually learn to harness and later recreate for itself? This is one of several theories we'll explore in detail in the next chapter, but I mention it now because it highlights something crucial. By the time Earth was 4 billion years old, it had created environments, many different environments where interesting chemistry could occur. There were the vents, with their gradients and mineral catalysts. There were tidal pools, periodically flooded and dried, concentrating organic compounds. There were volcanic lakes, acidic and rich in minerals. There were ocean surfaces, exposed to ultraviolet radiation and lightning. And there were clay surfaces and mineral grains, which could act as templates and catalysts for chemical reactions. Each of these environments had advantages and disadvantages for complex chemistry. The key insight is that Earth had become a vast natural laboratory, with billions of experiments running simultaneously in different conditions. And chemistry, when given the right ingredients, energy and time, does remarkable things. Let's talk about those ingredients. What chemicals were present in Earth's early oceans and atmosphere? Carbon was abundant, mostly as carbon dioxide in the atmosphere and dissolved in the oceans as carbonic acid and bicarbonate ions. Carbon is life's fundamental building block, the element around which all organic chemistry revolves. Its ability to form 4 strong bonds and create complex chains and rings makes it uniquely suited for building the molecules of life. Nitrogen was plentiful in the atmosphere, though mostly as inert N2 gas, which is very stable and difficult to react. However, lightning and volcanic activity could break these bonds, forming nitrogen oxides that dissolved in rain and washed into the oceans as nitrates and nitrites. Nitrogen is essential for amino acids and nucleotide bases, the building blocks of proteins and DNA. Hydrogen was everywhere, in water, in methane, in hydrogen sulfide from vents. Hydrogen is life's simplest atom, but its ability to form bonds with carbon, oxygen, nitrogen, and other elements makes it indispensable. Oxygen, paradoxically, was present but not as O2 gas. Instead, it existed in water, carbon dioxide, and various minerals. Free oxygen would come later, created by life itself in one of the most dramatic transformations Earth has ever seen. Phosphorus was less abundant but still present, eroded from rocks and concentrated in certain locations. Phosphorus is crucial for DNA, RNA, and ATP, the genetic code and energy currency of life. Without phosphorus, life as we know it couldn't exist. Sulfur was abundant, especially around volcanic zones and hydrothermal vents. Volcanic gases and vent fluids were rich in hydrogen sulfide and sulfur dioxide. Sulfur plays crucial roles in protein structure and in certain metabolic reactions. And then there were trace elements: iron, magnesium, calcium, zinc, molybdenum, and others. Many of these serve as cofactors in enzymes, the molecular machines that drive biochemical reactions. The availability of these metals in Earth's early oceans may have shaped the fundamental biochemistry that all life still uses today. What about organic molecules, compounds containing carbon-hydrogen bonds? Were these present before life began? The answer is almost certainly yes. Multiple sources could have delivered or created organic compounds. Meteorites and comets brought organic molecules from space. Even today, when we analyze certain meteorites, we find amino acids and other organic compounds. The famous Murchison meteorite, which fell in Australia in 1969, contained more than 90 different amino acids, only 19 of which are used by life on Earth. In Earth's atmosphere, lightning could spark reactions between methane, ammonia, and other gases, creating organic molecules that rained down into the oceans. This was famously demonstrated in the 1952 Miller-Urey experiment, where Stanley Miller and Harold Urey created a miniature version of Earth's early atmosphere in a flask, zapped it with electrical sparks to simulate lightning, and within days produced amino acids and other organic compounds. Hydrothermal vents could drive reactions between carbon dioxide and hydrogen, creating organic molecules through processes similar to the Fischer-Tropsch synthesis used in industry. The heat, mineral catalysts, and chemical gradients at vents create conditions favorable for building complex carbon-based molecules from simple starting materials. And volcanic activity itself could contribute. The hot gases and mineral surfaces around volcanoes can catalyze reactions that build organic molecules. Some researchers have even proposed that volcanic pumice, lightweight, porous volcanic rock, could have provided protected spaces where organic molecules could concentrate and react. So by 3.8 billion years ago, as the late heavy bombardment was winding down and Earth's surface was stabilizing, the stage was truly set. The planet had oceans, rich in dissolved minerals and laced with organic compounds. It had diverse environments, from scorching vents to cool surface waters, from tidal pools to open ocean. It had energy sources aplenty, and it had time, vast stretches of time for chemistry to experiment, to stumble forward through countless combinations of atoms and molecules. But something was still missing. All of these ingredients, all of this complexity was still just chemistry. It wasn't alive. It didn't reproduce, didn't evolve, didn't respond to its environment in the coordinated way that even the simplest bacterium does. Somewhere, somehow, chemistry had to cross a threshold. It had to begin organizing itself into systems that could maintain themselves, that could grow, that could make copies. It had to discover information storage, energy management, and self-replication. This is the most profound mystery in all of biology. How did non-living chemistry become living biology? How did molecules become organisms? How did the first cell arise? The honest answer is that we don't know for certain. We weren't there to observe it. We can't recreate exactly the conditions of early Earth. And the earliest life, being simple and soft, left little to no fossil evidence. The rocks that might contain the oldest signs of life have been heated, compressed, and chemically altered by billions of years of geological activity, destroying or obscuring the evidence. But we have clues. We have theoretical frameworks. We have experimental results. And we have the fact that life did arise, somehow, from this chemistry. Every living thing on Earth, every bacterium, every plant, every animal, every fungus shares the same basic biochemistry, uses the same genetic code, carries within its cells the echoes of that first origin. In the next chapter, we're going to dive deep into the chemistry of creation. We'll explore the leading theories of how life began, from the famous primordial soup idea to modern concepts involving mineral surfaces, self-replicating molecules, and the RNA world. We'll meet the molecules that started it all and try to understand the step-by-step process by which simple chemistry could have evolved into the first living cells. It's a detective story billions of years old, and while we may never have all the answers, the clues we do have paint a picture that's both scientifically rigorous and profoundly beautiful. Because what we're about to discover is that life isn't magic, isn't separate from chemistry and physics. It's chemistry and physics organizing themselves in increasingly complex ways, following the laws of nature to create something that appears, from the outside, to defy those very laws. The violent birth of Earth was complete. The habitable world had emerged. Now in its ancient oceans and among its volcanic shores, the next chapter of the story was about to begin. We've arrived at the most profound question in all of science. How did life begin? How did lifeless molecules, following nothing but the laws of chemistry and physics, organize themselves into something that could grow, reproduce, and evolve? How did we get from rocks and water to bacteria, and eventually to blue whales and human beings? This is the question of abiogenesis, life arising from non-life. And it's important to understand right from the start that this is not the same question as evolution. Evolution by natural selection, so brilliantly articulated by Charles Darwin, explains how life changes over time, how simple organisms become complex, how new species arise. But evolution requires life to already exist. It needs something that can reproduce, something that can pass on traits, something that can compete for resources. Abiogenesis asks the question that comes before. Where did that first reproducing thing come from? To answer this, we need to think about what life actually is. This might seem obvious. You know life when you see it, right? A dog is alive, a rock is not. But defining life precisely is remarkably difficult. Biologists have argued about this for centuries. Is a virus alive? It can reproduce, but only by hijacking living cells. What about a self-replicating computer program? It reproduces and evolves, but it's made of information, not molecules. For our purposes, let's use a working definition. Life is a self-sustaining chemical system capable of Darwinian evolution. This means it can maintain itself, using energy to stay organized against the natural tendency toward disorder. It can reproduce, making copies of itself. And crucially, it can evolve. It has heredity, variation, and selection. Even the simplest bacterium today is staggeringly complex. It has a cell membrane that separates inside from outside. It has DNA encoding thousands of genes. It has ribosomes that read those genes and make proteins. It has metabolic pathways that extract energy from its environment. It has regulatory systems that respond to changes. There's no way that something this complex could have arisen all at once. It's not just improbable, it's essentially impossible. The number of atoms that would need to come together in exactly the right configuration is astronomically large. As the astronomer Fred Hoyle famously, though wrongly, said, it would be like a tornado sweeping through a junkyard and assembling a Boeing 747. But Hoyle was wrong not because life isn't complex, but because he misunderstood how it arose. Life didn't appear all at once. It emerged gradually, through a series of steps, each one building on the last. And at each step, chemistry was doing what chemistry does, following the laws of physics, seeking lower energy states, forming bonds that are thermodynamically favorable. So let's start at the beginning with the simplest building blocks. Life as we know it is built from organic molecules, molecules based on carbon. And organic molecules, despite the name, don't require life to form. They can arise through purely chemical processes, and they were almost certainly present in Earth's early oceans. The most basic organic molecules are simple hydrocarbons, chains or rings of carbon atoms with hydrogen attached. Methane, CH4, is the simplest, but from there, complexity can grow. Add an oxygen atom and you get alcohols or aldehydes. Add nitrogen and you get amines. These simple molecules can link together to form larger ones. The building blocks of life fall into a few key categories. First, there are amino acids, small molecules with an amino group on one end and a carboxylic acid group on the other, with different chemical groups in between. Life uses 20 standard amino acids, stringing them together like beads on a necklace to make proteins, but amino acids can form abiotically without life. We know this because of one of the most famous experiments in the history of biology. In 1952, Stanley Miller was a young graduate student working with Harold Urey at the University of Chicago. They wanted to test whether organic molecules could form under conditions resembling early Earth. Miller built a simple apparatus, a sealed glass system with a flask of water representing the ocean, a chamber above it representing the atmosphere, electrodes to create sparks representing lightning, and tubes to circulate everything. He filled the atmosphere with methane, ammonia, hydrogen, and water vapor, gases that were thought at the time to be present on early Earth. Then he turned on the sparks and let it run. Within days, the water had turned a murky brown when Miller analyzed it. He found amino acids, glycine, alanine, aspartic acid, and others. Simple chemistry, given energy, had created the building blocks of proteins. Now, we should note that Earth's early atmosphere probably wasn't quite as reducing, as hydrogen-rich as Miller assumed. More likely, it was dominated by carbon dioxide and nitrogen. But later experiments have shown that even with more realistic atmospheric compositions, organic molecules still form when energy is added. Lightning, ultraviolet radiation, volcanic heat, and impact energy can all drive these reactions. And as I mentioned in the previous chapter, meteorites bring organic molecules from space. The Murchison meteorite contained amino acids, including many that life doesn't use, proof that these molecules can form through non-biological processes. In fact, everywhere we look in space, where there are organic molecules at all, we find amino acids. They seem to be a natural consequence of carbon chemistry. Beyond amino acids, life needs nucleotides, the building blocks of DNA and RNA. These are more complex, consisting of 3 parts, a sugar, ribose or deoxyribose, a phosphate group, and a nitrogenous base, adenine, guanine, cytosine, thymine, or uracil. Nucleotides link together to form the long chains of DNA and RNA that store genetic information. Can nucleotides form abiotically? This has been more controversial. The sugar component is tricky. Sugars are unstable and tend to break down quickly in water, especially at the warm temperatures likely present on early Earth. And the bases themselves, while they can form from simple starting materials like hydrogen cyanide, require specific conditions. However, recent research has shown promising results. John Sutherland and his colleagues demonstrated in 2009 that nucleotides could form through a series of reactions that bypass some of the difficult steps previously thought necessary. Starting with simple molecules like cyanoacetylene and glycolaldehyde, and using ultraviolet light as an energy source, they were able to create activated nucleotides, the chemical precursors that could polymerize into RNA. What this tells us is that while nucleotide synthesis is more challenging than amino acid synthesis, it's not impossible. Given the right conditions, the right chemicals, the right temperature, the right energy source, these crucial building blocks could have formed. Then there are lipids, fatty molecules that don't dissolve well in water. The most important of these are phospholipids, which have a water-loving, hydrophilic head and a water-repelling, hydrophobic tail. When these molecules are placed in water, they spontaneously organize into structures, micelles, bilayers, and vesicles. The vesicles are particularly interesting because they're basically tiny bubbles with a membrane made of 2 layers of lipids, the same basic structure as a cell membrane. This self-assembly is crucial. You don't need biology to make a membrane. Physics does it automatically. If you have fatty acids or phospholipids in water, and these compounds could have formed on early Earth or been delivered by meteorites, they will spontaneously create bubble-like structures. These could have served as the first protocells, containers that separated a distinct chemical environment inside from the outside world. And finally, there are sugars and carbohydrates. Simple sugars like ribose are part of RNA, while more complex carbohydrates can serve as energy storage or structural materials. The famous Formose reaction, discovered in 1861, shows that sugars can form from formaldehyde in the presence of mineral catalysts, though the reaction produces a messy mixture of many different sugars, not the specific ones life uses. So we have amino acids forming readily under a variety of conditions. We have nucleotides that can form through plausible prebiotic pathways. We have lipids that self-assemble into membrane structures. And we have sugars that can form through simple chemistry. But having the building blocks doesn't mean you have life. It's like having a pile of bricks, wood, and nails. You don't have a house yet. You need those materials to be organized in specific ways. You need them to work together as a system. This is where things get really interesting and really challenging, because modern life uses proteins to catalyze reactions, to speed them up and make them go in specific directions. Proteins are incredibly sophisticated molecular machines, folded into precise 3-dimensional shapes that allow them to grab onto specific molecules and transform them. But proteins are built by ribosomes, which read genetic information from RNA, which is copied from DNA, and DNA is copied and repaired by proteins. It's a chicken and egg problem. Which came first, proteins or genetic material? For a long time, this seemed like an insurmountable paradox. You need proteins to make DNA and RNA, but you need DNA or RNA to make proteins. How could either have arisen first? The answer, or at least the most promising answer we have, lies in a remarkable discovery made in the 1980s. Thomas Cech and Sidney Altman, working independently, discovered that RNA molecules can act as catalysts. They called these catalytic RNA molecules ribozymes. This was revolutionary because it meant that RNA could serve both functions. It could store genetic information like DNA, and it could catalyze reactions like proteins. Suddenly, a pathway became visible. Perhaps early life was based entirely on RNA, an RNA world where these molecules handled both information storage and catalysis. Only later did the more efficient division of labor evolve, with DNA taking over information storage and proteins taking over catalysis. We'll explore the RNA world hypothesis in much more detail in part 3 of this chapter. But for now, let's focus on the key insight. The building blocks of life can form through chemistry alone. Given the right starting materials, the right conditions and energy, complex organic molecules will form. Earth's early oceans were a vast chemical laboratory. In different locations around hydrothermal vents, in tidal pools, on mineral surfaces, in the open ocean, different reactions were occurring. Amino acids were forming and breaking down. Nucleotides were assembling and disintegrating. Lipids were creating and dissolving membrane structures. Most of these experiments went nowhere. The molecules formed, reacted, and broke apart. But chemistry is a numbers game. Given enough time, Enough variety of conditions, enough random combinations, something interesting was bound to happen. And what needed to happen was this: molecules needed to start making copies of themselves. Because once you have a molecule that can catalyze its own reproduction, you have the beginning of evolution. If that molecule makes copies with slight variations, and some of those variations are better at reproducing than others, then natural selection begins. The better replicators become more common. Complexity can start to accumulate. This concept, self-replication, is the crucial threshold that chemistry needs to cross to become biology. It's what separates a pile of organic molecules from a living system. And while we still don't know exactly how it happened, we have increasingly sophisticated ideas about where it might have occurred and what the first self-replicators might have looked like. But before we get to self-replication, we need to understand more about where all this chemistry was happening. Because location matters. The environment shapes what reactions are possible, what molecules can form, what systems can persist. In the next part of this chapter, we're going to explore the leading theories for life's origin, the different environments that scientists think could have cradled the first life. From Darwin's famous warm little pond to the dark, pressurized world of deep-sea hydrothermal vents, each location offers different advantages and faces different challenges. The question isn't just what molecules were present, but where they came together, how they were concentrated, and what energy sources drove them to organize into increasingly complex systems. Because life didn't begin everywhere. It began somewhere specific, in some particular environment that had just the right combination of factors. And once we understand those environments, we can begin to piece together the most likely pathway from chemistry to biology, from molecules to the first living cell. Charles Darwin, in a letter to his friend Joseph Hooker in 1871, engaged in a bit of speculation. He wrote, "It is often said that all the conditions for the first production of a living organism are now present which could ever have been present, but if, and oh, what a big if, we could conceive in some warm little pond, with all sorts of ammonia and phosphoric salts, light, heat, electricity, etc., present, that a protein compound was chemically formed ready to undergo still more complex changes." Darwin's warm little pond has become one of the most enduring images in origin of life research. It captures something essential. Life needed a place to begin, a location where chemicals could concentrate, react, and organize. But was it really a pond, or did life begin somewhere else entirely? Let's explore the major competing theories, each proposing a different environment for life's origin. The primordial soup theory, popularized by Soviet biochemist Alexander Oparin and British scientist J.B.S. Haldane in the 1920s, suggests that Earth's early oceans were rich in organic molecules, a soup of prebiotic compounds. Lightning, ultraviolet radiation, and other energy sources drove reactions that created increasingly complex molecules. Eventually, these molecules organized into primitive living systems. The Miller-Urey experiment seemed to support this idea. If you could create amino acids in a flask in a few days, imagine what billions of years of chemistry in an ocean could accomplish. The ocean is vast, providing enormous volume for reactions. It's relatively stable in temperature and pH, and it can concentrate molecules in certain locations through evaporation, freezing, or adsorption onto surfaces. But the primordial soup theory faces serious challenges. One is the dilution problem. Oceans are big, really big. If organic molecules are scattered throughout that volume, the concentration might be too low for the reactions needed to build complex systems. It's like trying to bake a cake by throwing flour, sugar, and eggs into a swimming pool. You need concentration. Another problem is energy. While the ocean surface receives sunlight and might be struck by lightning, most of the ocean is dark and relatively low energy. And many of the reactions needed to build complex molecules require energy input. They're not spontaneous. They need to be driven. Finally, there's the problem of competing reactions. Water is good at breaking down complex organic molecules, especially at warm temperatures. The same hydrolysis reactions that digest food in your stomach would have degraded complex molecules in the early ocean. Life needs to build up complexity faster than chemistry breaks it down. These challenges led researchers to look for more specific environments, places where concentration, energy, and protection from degradation might all be available. Enter the tidal pool hypothesis. Instead of the open ocean, imagine shallow pools of water at the shoreline, periodically filled by tides and then left to evaporate. As water evaporates, molecules concentrate. Sunlight provides energy. The wet-dry cycling might even help certain reactions, particularly the formation of polymers, chains of molecules linked together. Modern experiments have shown that wet-dry cycling can promote the formation of peptides, short chains of amino acids, and nucleotides. When concentrated and then dried, these molecules can link together in ways that don't happen readily in dilute solution. The surface of the pool, perhaps lined with clay or other minerals, can provide catalytic surfaces that facilitate reactions. David Deamer, a prominent origin of life researcher, has championed a version of this idea, demonstrating that lipid membranes can self-assemble in tidal pool conditions and that these membranes can encapsulate other molecules, creating protocells, primitive cell-like structures. But tidal pools have their own problems. They're small and temporary. They're exposed to harsh ultraviolet radiation, which can damage complex molecules, and they're vulnerable to environmental changes. A storm, a landslide, or a shift in sea level could destroy them. This brings us to perhaps the most popular current theory, the deep-sea hydrothermal vent hypothesis. And this is where things get truly fascinating. Imagine a crack in the ocean floor, 2 kilometers deep, far below the reach of sunlight. Cold seawater seeps down through the rock, gets heated by magma below, reacts with the minerals, and then jets back up, hot and laden with dissolved chemicals. As this hot alkaline water meets the cold acidic ocean water, minerals precipitate out, forming chimney-like structures that can tower tens of meters above the seafloor. These are hydrothermal vents, and they're some of the most geologically and chemically dynamic places on Earth. Today, they support entire ecosystems based not on photosynthesis, but on chemosynthesis, bacteria that extract energy from the chemical gradients between vent fluids and seawater, and animals that either feed on those bacteria or host them in their tissues. But could these vents have been the birthplace of life itself? The hypothesis was first seriously proposed by Günther Westershäuser in the 1980s and has been developed by many researchers since, including Mike Russell and Bill Martin. The key insight is that hydrothermal vents provide several things that life needs. First, concentration. As minerals precipitate around the vent, they create porous structures riddled with tiny compartments. These natural chambers can trap and concentrate organic molecules, solving the dilution problem. Second, energy. The chemical gradients between vent fluids and ocean water represent stored energy. Reduced chemicals like hydrogen and hydrogen sulfide in the vent fluids can react with oxidized chemicals like carbon dioxide in the seawater, releasing energy. This is exactly the kind of chemistry that drives metabolism in modern microbes. Third, catalysts. The mineral surfaces around vents, particularly iron-sulfur minerals, can catalyze organic reactions. Interestingly, many modern enzymes, the protein catalysts that drive biochemistry, have iron-sulfur clusters at their active sites. This might not be a coincidence. Life might have first used mineral catalysts and later evolved proteins to do the same job more efficiently. Fourth, protection. Deep underwater, organic molecules are shielded from destructive ultraviolet radiation. The temperature, while warm, isn't so hot as to immediately destroy complex molecules, especially at vents like Lost City, which operate at moderate temperatures. And fifth, most intriguingly, there's the proton gradient. Modern cells generate energy through a process called chemiosmosis. They pump protons, hydrogen ions, across a membrane, creating a gradient, and then let those protons flow back through a molecular machine called ATP synthase, which captures that energy to make ATP. This is how you extract energy from food. This is how plants capture sunlight. It's arguably the most fundamental energy process in all of biology. And remarkably, alkaline hydrothermal vents naturally create proton gradients across thin mineral membranes. The resemblance to cellular bioenergetics is striking. Nick Lane and Bill Martin have argued that this isn't coincidence, that life arose in these mineral compartments, exploiting natural proton gradients, and only later evolved the machinery to create its own gradients independently. In this view, the deep-sea vent isn't just a favorable location for life's origin, its chemistry shaped the fundamental energy metabolism that all life still uses. But vents aren't the only game in town. Some researchers favor volcanic pools or geothermal fields on land, places where volcanic heat, mineral-rich water, and atmospheric gases mix. These environments offer similar advantages to underwater vents, but with the addition of wet-dry cycling and access to atmospheric gases. Others have proposed that life began on mineral surfaces in general, regardless of the specific environment. Clay minerals in particular have interesting properties. They have layered structures that can absorb organic molecules, concentrating them on surfaces. They can catalyze certain reactions, and they can even template the formation of polymers, encouraging molecules to line up and link together. Alexander Graham Cairns Smith famously proposed that life might have begun as self-replicating clay crystals, with organic molecules only later taking over the replicative role. While this specific idea hasn't gained wide acceptance, the broader concept that mineral surfaces played a crucial role in organizing early chemistry remains influential. There's even the panspermia hypothesis, the idea that life didn't originate on Earth at all, but arrived from space, perhaps on meteorites or comets. While this might seem like science fiction, we know that hardy bacteria can survive in space for extended periods, that organic molecules are common in meteorites, and that material is regularly exchanged between planets through impacts. However, panspermia doesn't solve the origin of life problem, it just moves it elsewhere. If life came from Mars or another planet, how did it originate there? At some point somewhere, life had to arise from non-life. So which hypothesis is correct? The honest answer is that we don't know. Each has strengths and weaknesses. Each is supported by some experimental evidence and challenged by other findings. And it's entirely possible that the truth involves elements of multiple theories, perhaps organic molecules formed in the atmosphere and rained into the ocean, as the primordial soup theory suggests. Perhaps they concentrated in tidal pools or around vents. Perhaps mineral surfaces catalyzed key reactions. Perhaps different components of life arose in different places and later came together. What we can say is this: Earth's early environment was chemically diverse, with many different microenvironments offering different conditions. Somewhere, perhaps in many different somewheres, the right combination of factors came together. Organic molecules concentrated, energy drove reactions, polymers formed, and crucially, some of those polymers began to catalyze their own formation. Because that's the real breakthrough we're looking for: self-replication. A molecule or system of molecules that can make copies of itself. Because once you have that, you have the raw material for evolution. And this brings us to the RNA world, perhaps the most important conceptual framework in origin of life research. The idea is simple but profound. Before there was DNA and proteins, there was RNA doing both jobs. RNA stored information and catalyzed reactions. It was the first genetic material and the first enzyme. This solves the chicken and egg problem. You don't need proteins to make RNA or RNA to make proteins, if RNA can make itself. But how would an RNA world arise? What would it look like? And how would it transition into the DNA protein world of modern life? These are the questions we'll tackle in the next and final part of this chapter. We're going to dive into the molecular details of self-replication, explore how natural selection could operate at the molecular level, and trace the steps from simple self-replicating molecules to the first true cells we're going to witness, as best as current science allows, the actual moment when chemistry became biology. Because that moment, whenever and wherever it occurred, changed everything. It set in motion a process that has run continuously for nearly 4 billion years, producing every living thing that has ever existed. It turned Earth from a lifeless ball of rock and water into a living world, covered in a thin film of biology that has reshaped the planet's surface, atmosphere, and oceans. And it all began with molecules learning to copy themselves. We've arrived at the heart of the mystery. How did molecules become alive? How did chemistry cross that threshold into biology? The answer, scientists increasingly believe, lies in a molecule called RNA. RNA ribonucleic acid is famous as DNA's helper. In modern cells, DNA stores the genetic information, but RNA carries that information from the nucleus to the ribosome, where it's used to build proteins. RNA is the messenger, the intermediary, the go-between. But RNA is much more than that. It's versatile in a way that DNA isn't. RNA can fold into complex three-dimensional shapes, creating pockets and grooves that can bind to other molecules. And crucially, some RNA molecules can act as catalysts, ribozymes, as we mentioned earlier. They can speed up chemical reactions, including reactions that involve RNA itself. This dual capability, information storage and catalysis, is why RNA is central to most origin of life theories. If a molecule can both carry genetic information and catalyze reactions, including its own replication, then you have the ingredients for a self-sustaining, evolving system. Welcome to the RNA world. The RNA world hypothesis, developed by Walter Gilbert, Leslie Orgel, and others in the 1980s, proposes that early life was based entirely on RNA. Before DNA, before proteins, there was a period when RNA-based organisms or proto-organisms dominated Earth. These entities would have had RNA genomes and RNA enzymes. Only later did DNA take over genetic storage, being more stable, and proteins take over catalysis, being more versatile. The evidence for an RNA world is compelling. First, modern cells still use RNA in central roles. Ribosomes, the molecular machines that make proteins, are largely built from RNA. The catalytic activity, the part that actually forms the peptide bonds linking amino acids together, is performed by RNA, not protein. This suggests that ribosomes are molecular fossils, relics of an earlier RNA-based metabolism. Second, modern metabolism uses several RNA-based molecules in crucial roles. ATP, the energy currency of the cell, is essentially an RNA nucleotide with extra phosphate groups. Many enzyme cofactors, helper molecules that enzymes need to function, are based on RNA nucleotides. This suggests that these molecules date back to the RNA world and have been retained even as the rest of metabolism evolved. Third, we've discovered that RNA can do things we never imagined. Researchers have created ribozymes that can copy short RNA sequences, link amino acids together, modify themselves, and even create new ribozymes. While we haven't yet created a fully self-replicating RNA system in the lab, we're getting closer. But let's think about what an RNA world would actually look like. How would it get started? First, you need RNA nucleotides, the building blocks. As we discussed earlier, these can form through plausible prebiotic chemistry, though the pathway is challenging. Let's assume that somehow, in some favorable environment, you have a concentration of activated nucleotides molecules ready to link together. In the right conditions, nucleotides can spontaneously polymerize, linking into chains. This has been demonstrated in laboratory experiments, particularly on mineral surfaces or in the presence of certain metal ions that act as catalysts. You'd get random sequences of varying lengths, most of them doing nothing interesting. But here's where it gets interesting. Some of those random sequences might fold into shapes that have weak catalytic activity. Perhaps 1 in a million random sequences can bind to a nucleotide and help it link to another nucleotide. That's not much, but it's a start. If that weak ribozyme happens to catalyze reactions that make more of itself, if it can help copy its own sequence, then you have the beginnings of self-replication. It doesn't have to be perfect. It doesn't have to be fast. It just has to work well enough that this particular sequence becomes more common than random sequences. And once you have self-replication, you have evolution. Because no replication process is perfect. Mistakes happen. Sometimes a wrong nucleotide gets incorporated. Most of these mutations will break the ribozyme, making it non-functional. But occasionally, a mutation might make it better, more efficient at replication, more stable, better at competing for nucleotides. Natural selection begins to operate. The better replicators become more common. Complexity can accumulate. Additional functions can evolve, perhaps the ability to make the nucleotide building blocks, or to create protective structures, or to extract energy from the environment more efficiently. This is molecular evolution, and it operates by the same principles as biological evolution: variation, heredity, and selection. The sequences that are best at making copies of themselves come to dominate. Over time, the RNA world would have become more sophisticated. Networks of interacting ribozymes might have emerged, each performing different functions, but working together as a system. Some might have catalyzed the synthesis of nucleotides. Others might have specialized in replication. Still others might have developed the ability to link amino acids together, creating the first simple proteins. Why would RNA bother making proteins? Because proteins, built from 20 different amino acids instead of 4 nucleotides, can fold into a far greater variety of shapes and perform catalysis more efficiently. An RNA-based system that could recruit proteins to help it would have a huge advantage over one relying on RNA alone. Similarly, DNA is more stable than RNA. The extra oxygen atom in RNA makes it more reactive and prone to degradation. A system that stored its genetic information in DNA but used RNA to access that information would be more reliable, making fewer errors over time. So gradually through evolution, we'd transition from pure RNA to the DNA-RNA protein world of modern cells. But we're getting ahead of ourselves. We still need to address a crucial question. How did these replicating molecules get enclosed in cells? Modern cells are separated from their environment by membranes, lipid bilayers that create a distinct inside and outside. This compartmentalization is crucial for life. It allows the cell to maintain different chemical conditions inside than outside. It concentrates molecules, making reactions more efficient. And it creates a unit of selection. Either the whole cell survives and reproduces, or it doesn't. But how did early replicators get enclosed in membranes? The answer might be surprisingly simple. Lipids self-assemble. As we discussed earlier, when fatty acids or phospholipids are placed in water, they spontaneously form structures: micelles, bilayers, vesicles. No biology required, just physics and chemistry. Experiments by Jack Szostak and others have shown that these lipid vesicles can grow, incorporating new lipid molecules from the environment. They can divide, splitting into daughter vesicles when mechanical forces like wave action act on them. And crucially, they can encapsulate RNA and other molecules. Imagine this scenario: somewhere on early Earth, perhaps in a tidal pool or around a hydrothermal vent, RNA molecules are replicating. Lipids are also present, forming vesicles. Some RNA molecules, by chance, get encapsulated inside vesicles. This encapsulation provides benefits. The RNA is protected from the environment. Nucleotides and other molecules that diffuse into the vesicle are concentrated, making replication more efficient. And now, selection operates at a new level, not just on individual RNA molecules, but on entire protocells. A vesicle containing RNA that's good at replicating will accumulate more RNA. This might cause the vesicle to grow and eventually divide, creating daughter vesicles that also contain that RNA. Vesicles with less efficient RNA won't reproduce as effectively. Over time, more efficient protocells come to dominate. This is the beginning of cellular life, membrane-enclosed compartments containing self-replicating genetic material. They're not yet true cells. They don't have the sophisticated machinery of modern bacteria, but they're recognizably alive in that they can grow, reproduce, and evolve. What happens next is a process of incremental improvement. Random mutations in the RNA lead to new capabilities. Perhaps one mutation allows the RNA to catalyze the synthesis of more lipids, helping the vesicle grow. Another might improve nucleotide synthesis, making replication faster. Yet another might create a simple protein that performs some useful function. Each improvement that increases the protocell's ability to survive and reproduce will be favored by natural selection. Complexity accumulates. The system becomes more integrated, more efficient, more robust. At some point, the system develops the ability to make proteins systematically, the origin of the genetic code. This is one of the great mysteries still being researched. How did specific nucleotide sequences come to specify specific amino acids? How did the ribosome evolve? Why this particular code and not some other? We don't have complete answers, but we have clues. The genetic code is nearly universal. Almost all life uses the same code, suggesting it evolved very early and has been preserved ever since. Some researchers have proposed that the code evolved based on chemical affinities between certain amino acids and certain nucleotide sequences. Others suggest it was largely random, but became frozen in place once evolution had built complex systems around it. Regardless of the details, once the code was established, evolution could operate much more efficiently. Now, changes in RNA sequences would produce predictable changes in proteins, allowing much more sophisticated optimization of molecular machines. DNA likely entered the picture relatively late. It offers more stable long-term storage than RNA, but it requires dedicated enzymes to replicate and transcribe. An RNA-based system would need to evolve these enzymes before DNA could take over. But once it did, the advantages were clear enough that DNA became the universal genetic material. So here's the picture that emerges. Life began with self-replicating RNA molecules, possibly assisted by mineral catalysts, in some favorable environment on early Earth. These molecules became enclosed in lipid membranes, creating protocells. Over time, these protocells evolved more sophisticated metabolism, the ability to synthesize proteins, and eventually DNA-based genetic storage. This wasn't a quick process. It likely took hundreds of millions of years to progress from the first self-replicating molecules to anything resembling a modern cell. And the path certainly wasn't smooth. Many different protocell lineages probably arose and went extinct before one lineage hit upon the winning combination of features that would lead to all subsequent life. But by about 3.8 billion years ago, and possibly earlier, true cellular life existed on Earth. We know this because we find chemical signatures in ancient rocks that are best explained by biological activity. We find structures in rocks that look like fossilized microbial mats. And we find that all modern life shares fundamental biochemistry. The same genetic code, the same basic metabolic pathways, the same membrane structure, suggesting a common ancestor. That common ancestor is sometimes called LUCA, the last universal common ancestor. It wasn't the first living thing, it was the ancestor of all living things that still have descendants today. Other lineages may have existed earlier, but left no descendants. LUCA was probably already quite sophisticated. It had DNA, RNA, and proteins. It had a membrane, metabolic pathways, and the ability to reproduce. But it was still just a single-celled organism, microscopic and simple compared to the vast diversity of life that would later evolve. And that evolution from single cells to the incredible complexity and diversity of life we see today is the story of our next chapter. We're going to trace the epic journey from those first cells to the tree of life in all its magnificent branches. We'll see how simple bacteria transformed the planet's atmosphere, making it breathable for complex life. We'll witness the origin of complex cells, of multicellular organisms, of all the kingdoms and domains of life. Because life, once it began, didn't stand still. It evolved, adapted, radiated into every available niche on Earth. It survived catastrophes, mass extinctions, ice ages, and asteroid impacts. It developed photosynthesis, sex, predation, cooperation, and consciousness. It turned Earth from a barren rock into a living world, and in doing so, it created the conditions for its own continued evolution. The chemistry of creation had crossed the threshold into biology. Now biology would show what it could do with 4 billion years to work with. Life had begun. Somewhere in Earth's ancient oceans, perhaps 3.8 billion years ago, or even earlier, the first true cells were going about their business, absorbing nutrients, growing, dividing, evolving. These were simple organisms, single-celled and microscopic, but they were unmistakably alive. They had crossed the threshold from chemistry to biology, and now they were poised to inherit the Earth. But what did these first cells look like? What were they capable of? And how do we know anything about organisms that lived so long ago, leaving barely a trace of their existence? Let's start with what we can infer about early life from the fossil record and from studying modern organisms. The earliest convincing evidence of life comes from rocks in Greenland and Australia dating to about 3.7 to 3.8 billion years ago. These rocks contain chemical signatures, specific ratios of carbon isotopes, that strongly suggest biological activity. Living things prefer lighter carbon isotopes when they build organic molecules, and these ancient rocks show exactly that preference. Slightly younger rocks, around 3.5 billion years old, contain structures called stromatolites, layered formations created by communities of microorganisms, particularly cyanobacteria. Remarkably, stromatolites still form today in a few places like Shark Bay in Australia, built by bacterial mats that trap sediment and grow in layers. The ancient stromatolites look virtually identical to modern ones, suggesting that even 3.5 billion years ago, microbial communities were sophisticated enough to build complex structures. But fossils only tell us so much. To understand early life, we also look at modern organisms, particularly bacteria and archaea, the two domains of single-celled life that diverged very early in evolutionary history. All life on Earth falls into three domains: bacteria, archaea, and eukarya. Bacteria and archaea are both prokaryotes. They lack a nucleus and other membrane-bound organelles. Eukarya includes everything else: protists, fungi, plants, and animals. All eukaryotic cells have a nucleus containing their DNA, along with specialized compartments like mitochondria for energy production. By comparing the DNA sequences of organisms from all three domains, scientists can reconstruct evolutionary relationships and trace back toward LUCA, the last universal common ancestor. What they find is fascinating. LUCA was probably similar to modern bacteria or archaea, single-celled without a nucleus, but with a complete set of genes for basic cellular functions. Interestingly, LUCA seems to have lived in a hot environment, possibly around hydrothermal vents. Many of its inferred genes are similar to those found in modern thermophiles, heat-loving microorganisms. This supports the idea that life may have originated in volcanic or hydrothermal settings where temperature and chemical gradients provided energy. From LUCA, life quickly diversified. Within a few 100 million years, quick on geological timescales, even if unimaginably long to us, bacteria and archaea had evolved a stunning variety of metabolic strategies. They colonized every available environment. Hot springs, deep ocean, shallow seas, sediments, even solid rock kilometers beneath the surface. Let's talk about metabolism, because this is where early life really showed its creativity. Modern animals, including humans, are boringly uniform in how we get energy. We eat organic molecules made by other organisms, combine them with oxygen, and extract energy through cellular respiration. But bacteria and archaea have evolved dozens of different metabolic strategies, and most of these probably arose very early in life's history. Some bacteria are chemolithotrophs. They extract energy from inorganic chemicals, not organic molecules. They might oxidize hydrogen, sulfur, iron, or ammonia, using the released energy to power their metabolism. This doesn't require any other organisms or even sunlight. It's life powered purely by geochemistry. Other bacteria are phototrophs. They capture energy from sunlight. But not all photosynthesis is the same. Modern plants and cyanobacteria perform oxygenic photosynthesis, splitting water molecules and releasing oxygen as a byproduct. But there are older forms of photosynthesis that use different electron donors, hydrogen sulfide instead of water, for example, and don't produce oxygen. These anoxygenic photosynthetic bacteria probably evolved first, perhaps as early as 3.5 billion years ago. They could harness sunlight without producing the highly reactive, potentially toxic oxygen. They flourished in shallow waters, where sunlight penetrated but sulfur compounds were abundant, particularly near volcanic zones. Then there are methanogens, archaea, that produce methane as a metabolic byproduct. They take hydrogen and carbon dioxide and produce methane and water, extracting energy from the reaction. Methanogens are anaerobic. They're poisoned by oxygen. They probably were very common in Earth's early oceans and still thrive today in oxygen-free environments like swamps, deep ocean sediments, and the guts of animals. And we can't forget the acetogens, sulfate reducers, iron reducers, and the bewildering variety of other metabolic types. The point is this: early bacteria and archaea were not just passively floating in the ocean, barely scraping by. They were dynamic, innovative, constantly evolving new ways to extract energy from their environment. This metabolic diversity had profound implications. It meant that life wasn't limited to specific locations or resources. Bacteria could colonize virtually anywhere liquid water existed and where some source of chemical energy was available. Life spread across the planet into every crack and crevice, every pool and ocean, every hot spring and cold seep. But life was still microscopic, still simple, still single-celled. The Earth, 3 billion years ago, would have looked barren from space. No green continents, no forests, no visible life at all. Yet beneath the ocean surface and in the shallow waters, life was everywhere, transforming the chemistry of the planet in subtle but important ways. One of the most significant early innovations was nitrogen fixation, the ability to take nitrogen gas from the atmosphere and convert it into ammonia, which can then be used to build amino acids and other nitrogen-containing molecules. Nitrogen gas is abundant but very stable. Breaking the triple bond between the two nitrogen atoms requires significant energy. Some bacteria evolved nitrogenase enzymes capable of doing this. Nitrogen fixation is metabolically expensive, but it opened up a virtually limitless supply of nitrogen. Organisms no longer had to compete for the limited nitrogen available in minerals or other sources. This innovation, probably arising early in bacterial evolution, allowed life to expand dramatically. Another crucial innovation was the evolution of more efficient cellular machinery. Early cells were probably leaky and inefficient, with poorly regulated metabolism. But natural selection favored improvements. More efficient enzymes evolved. Better membranes developed. Regulatory systems arose that could sense environmental conditions and adjust metabolism accordingly. And crucially, horizontal gene transfer became common. Unlike animals, which primarily inherit genes from their parents, bacteria can acquire genes directly from other bacteria, even from different species. A bacterium might pick up DNA from its environment, released by dead cells, and incorporate useful genes into its own genome, or two bacteria might physically connect and transfer genes. This meant that beneficial innovations could spread rapidly through bacterial populations and even between different lineages. If one bacterium evolved an enzyme that could break down a new food source, other bacteria could acquire that gene and gain the same ability. Evolution could proceed much faster than if every lineage had to reinvent every innovation independently. The early Earth was thus a microbial world, dominated by bacteria and archaea engaged in complex ecological relationships. Some cooperated, living in communities where the waste products of one species fed another. Others competed, evolving antibiotics and other chemical weapons to kill rivals. Some became parasites, invading other cells and exploiting their resources. And all of this was happening beneath an atmosphere that would have been toxic to most modern life. Remember, there was still essentially no oxygen in the air. The atmosphere was dominated by nitrogen, carbon dioxide, methane, and water vapor. Volcanic activity continued to pump out gases. The sky might have had a hazy orange appearance due to organic hazes in the atmosphere, similar to Saturn's moon Titan. But this was about to change, because somewhere in this microbial soup, one lineage of bacteria was about to stumble upon an innovation so powerful, so transformative, that it would fundamentally reshape the planet. This innovation was oxygenic photosynthesis, the ability to split water molecules, use the electrons to fix carbon dioxide into organic matter, and release oxygen as a waste product. It would be performed by cyanobacteria, and it would trigger one of the greatest environmental catastrophes and one of the greatest opportunities in Earth's history. But we're getting ahead of ourselves. Before we discuss the oxygen revolution, we need to understand just how successful bacteria had become. By 3 billion years ago, bacteria had spread across the planet. They lived in the oceans, in sediments, around hydrothermal vents, in hot springs, in shallow pools. They had diversified into countless species, each adapted to specific environments and lifestyles. The total biomass of bacteria was probably already substantial, perhaps comparable to modern bacterial biomass, and bacteria were beginning to significantly alter their environment. Their metabolic activities were changing the chemistry of the oceans and atmosphere. They were forming extensive mats and biofilms, creating local ecosystems of considerable complexity. In shallow waters, microbial mats could be centimeters thick, composed of multiple layers of different bacteria. At the surface, photosynthetic bacteria would capture sunlight. Below them, other bacteria would consume the organic matter produced by the photosynthesizers or extract energy from chemical gradients within the mat. Deeper still, anaerobic bacteria would thrive in the oxygen-free interior. These mats were remarkably sophisticated communities, with different species occupying different niches, engaged in complex metabolic interactions. They were Earth's first ecosystems, demonstrating that even without multicellular organisms, life could organize into structured, interdependent communities. And these communities were beginning to leave their mark on the geological record. The stromatolites I mentioned earlier are the fossilized remains of these microbial mats. They grew slowly, trapping sediment and precipitating minerals, building up layer upon layer over years and decades and centuries. Some stromatolites grew to be meters tall, massive structures built entirely by microscopic organisms. Bacteria were also beginning to influence the formation of minerals. Certain bacteria can precipitate calcium carbonate, forming limestone. Others can precipitate iron oxides or silica. The interaction between life and geology was becoming increasingly important, a theme that would only intensify as life evolved. But for all their success, for all their metabolic sophistication and ecological complexity, bacteria remained small and simple. They had no internal compartments beyond their single membrane. Their DNA floated freely in the cytoplasm, not enclosed in a nucleus. They reproduced by simple cell division, with each daughter cell essentially identical to the parent. They were, in short, fundamentally limited in the complexity they could achieve. The jump from bacteria to the kind of complex cells that would eventually give rise to plants, animals, and fungi would require a revolution in cellular architecture, a revolution we call the evolution of eukaryotic cells. But before that revolution could occur, the stage needed to be set. And setting that stage would require transforming Earth's atmosphere from an oxygen-free environment to one where oxygen was abundant. It would require the evolution of cyanobacteria, the development of oxygenic photosynthesis, and a global environmental transformation so profound that scientists call it the Great Oxidation Event. It would be a catastrophe for most existing life, a mass extinction that wiped out organisms across the planet. But it would also be an opportunity, creating conditions that would allow life to reach new levels of complexity and size. It would provide the energy-rich atmosphere that would eventually support animals, including, billions of years later, human beings capable of wondering about their origins. The rise of bacteria had set the stage. Now, one particular group of bacteria was about to change everything. Picture the Earth 2.5 billion years ago. The planet had been teeming with bacterial life for perhaps more than 1 billion years. The oceans were full of microorganisms. Microbial mats carpeted shallow seafloors. Life had adapted to nearly every available environment. But if you could somehow sample the atmosphere, you would find essentially no free oxygen. Perhaps tiny traces, created by the ultraviolet splitting of water vapor and quickly consumed by reactions with iron and other minerals, but nothing like the 21% oxygen we breathe today. This was about to change, and the change would be so dramatic, so consequential, that it's difficult to overstate its importance. Life was about to poison itself, and in doing so, open up entirely new possibilities. The culprits were cyanobacteria, sometimes called blue-green algae, though they're not algae at all, but true bacteria. At some point, we're not exactly sure when, but probably between 3 and 2.5 billion years ago, cyanobacteria evolved oxygenic photosynthesis. Let me explain what makes this so special. As I mentioned earlier, photosynthesis itself wasn't new. Various bacteria had already evolved the ability to capture sunlight and use its energy to fix carbon dioxide into organic molecules. But these earlier forms of photosynthesis used electron donors like hydrogen sulfide or ferrous iron. When these molecules are abundant, photosynthesis works fine. But when they run out, photosynthesis stops. Cyanobacteria discovered something revolutionary. They could use water as an electron donor. Water is everywhere. The oceans are full of it. Using water meant that photosynthesis would never be limited by the availability of electron donors. It was an almost unlimited energy source, but there was a cost. Splitting water molecules produces oxygen as a waste product. And oxygen is reactive, dangerously so. It can damage proteins, lipids, and DNA through oxidation reactions. For bacteria evolved in an oxygen-free world, oxygen was toxic. At first, this probably wasn't a major problem. The oxygen produced by early cyanobacteria was quickly consumed by chemical reactions with dissolved iron, sulfur, and other reduced substances in the ocean. Iron particularly acted as an enormous oxygen sink. When oxygen met dissolved ferrous iron, it oxidized it to ferric iron, which precipitated out of solution as rust. This process created some of the most spectacular geological formations on Earth, banded iron formations. These are layered rocks, alternating between iron-rich and iron-poor bands, found in ancient rock formations around the world. They represent billions of tons of iron that was once dissolved in the oceans and was precipitated out by oxygen from cyanobacterial photosynthesis. The banded iron formations are a record of this gradual oxygenation. For perhaps hundreds of millions of years, oxygen was produced but immediately consumed. The oceans and atmosphere remained anoxic. Cyanobacteria spread and diversified, forming extensive mats and dominating shallow water environments where sunlight was available. but eventually the oxygen sinks became saturated. The dissolved iron was mostly gone. The reduced gases from volcanoes and vents couldn't keep up with oxygen production, and oxygen began to accumulate in the atmosphere. This is the Great Oxidation Event, or GOE, occurring around 2.4 to 2.3 billion years ago. Within perhaps a few tens of millions of years, geologically rapid, atmospheric oxygen rose from trace levels to perhaps 1 to 2% of modern levels. This might not sound like much, but it was enough to fundamentally transform the planet. For anaerobic organisms, the vast majority of life at the time, this was a catastrophe. Oxygen damaged their cellular machinery. They retreated to oxygen-free environments, deep sediments, the guts of other organisms, anywhere oxygen couldn't penetrate. Many lineages probably went extinct entirely. This was likely Earth's first mass extinction, though calling it that might be misleading. Mass extinction implies a sudden die-off, but the GOE probably took millions of years. Still, it represented a fundamental reorganization of life on Earth. The anaerobes that had dominated for over a billion years were pushed to the margins. The future would belong to organisms that could tolerate, or better yet, exploit oxygen. But the GOE had other consequences too. Oxygen in the atmosphere reacted with methane, a potent greenhouse gas that had been keeping Earth warm despite the faint young sun. As methane levels dropped, Earth's temperature plummeted. The planet entered a series of glaciations so severe that ice may have covered the entire globe, from poles to equator, a snowball Earth. These glaciations, occurring around 2.3 billion years ago, were the most extreme in Earth's history. The planet looked nothing like the vibrant blue and green world we know. It was a white ball of ice, with perhaps only a few patches of open water near the equator or around volcanic zones. Life survived, almost certainly, but it must have been pushed to the brink. Eventually, volcanic activity built up enough carbon dioxide in the atmosphere to create a greenhouse effect strong enough to melt the ice. Earth thawed and life recovered. But it emerged into a fundamentally different world, one with oxygen. And here's where evolution showed its remarkable power to turn adversity into opportunity. Some organisms evolved not just to tolerate oxygen, but to use it. They developed aerobic respiration, a metabolic pathway that uses oxygen to extract far more energy from organic molecules than anaerobic processes can manage. Think about it this way. Anaerobic metabolism, like fermentation, might extract a few molecules of ATP from each glucose molecule. Aerobic respiration, using oxygen, can extract 30 or more. This isn't a marginal improvement, it's a revolution in energy efficiency. Organisms that could breathe oxygen had access to far more energy than their anaerobic competitors. They could grow faster, be more active, maintain more complex cellular structures. This energy bonanza would prove crucial for the next major transition in evolution, the origin of complex cells. Let's talk about eukaryotic cells. These are fundamentally different from bacteria and archaea. As I mentioned, eukaryotic cells have a nucleus, a membrane-bound compartment containing the DNA. They also have other membrane-bound organelles, mitochondria for energy production, endoplasmic reticulum for protein synthesis, Golgi apparatus for packaging and modifying proteins, and in plants, chloroplasts for photosynthesis. Eukaryotic cells are larger, typically 10 to 100 times the diameter of bacterial cells, which means hundreds to thousands of times the volume. They're more complex, with intricate internal architecture and the ability to perform sophisticated behaviors like engulfing food particles or moving using cilia and flagella. All complex life, all animals, plants, fungi, and the diverse group of single-celled organisms called protists are eukaryotes. We are eukaryotes. Every cell in your body is a eukaryotic cell. But how did eukaryotic cells evolve? This is one of the most fascinating stories in evolutionary biology, and it centers on an event called endosymbiosis. The story begins with mitochondria, the powerhouses of the cell. Mitochondria are where aerobic respiration occurs, where oxygen is used to extract energy from food. Every eukaryotic cell has them, or at least descended from ancestors that had them. Here's the remarkable thing. Mitochondria have their own DNA, separate from the nucleus. This DNA is circular, like bacterial DNA. Mitochondria replicate independently, dividing within the cell. And when scientists compared mitochondrial DNA to bacterial DNA, they found something astonishing. Mitochondria are most closely related to a group of bacteria called alpha proteobacteria. The explanation is endosymbiosis. At some point, probably around 2 billion years ago, an ancestral archaeal cell engulfed an alpha proteobacterium. But instead of digesting it, the two formed a symbiotic relationship. The bacterium, safely inside its host, used oxygen to produce energy. The host cell benefited from this energy production and provided the bacterium with protection and resources. Over time, the relationship became obligate. Neither could survive without the other. The bacterium lost many genes functions that the host cell could provide and transferred other genes to the host nucleus. It became an organelle, an integral part of the eukaryotic cell, the mitochondrion. This endosymbiotic event was transformative. It gave the proto-eukaryotic cell access to the energy benefits of aerobic respiration without having to evolve that machinery itself. The energy bonanza from mitochondria may have enabled the evolution of larger cell size and greater complexity, but endosymbiosis didn't stop there. Later, some eukaryotic cells engulfed cyanobacteria, which became chloroplasts, the organelles that perform photosynthesis in plants and algae. Like mitochondria, chloroplasts have their own circular DNA, resemble bacteria in size and structure, and clearly originated as free-living cyanobacteria. This means that photosynthesis in plants isn't really plant metabolism at all. It's the metabolism of the cyanobacterial endosymbionts that plants carry in their cells. When you look at a leaf, you're looking at billions of former cyanobacteria, now domesticated as chloroplasts, still doing what their ancestors did billions of years ago, capturing sunlight and fixing carbon. The evolution of eukaryotic cells, with their mitochondria and sometimes chloroplasts, set the stage for all subsequent complex life. But eukaryotes didn't just arise and immediately dominate. For perhaps a billion years, from about 2 billion to 1 billion years ago, eukaryotic cells existed but remained single-celled and relatively simple. This period is sometimes called the boring billion because evolution seems to have slowed down. Oxygen levels in the atmosphere remained low, perhaps 1 to 10% of modern levels. Life existed, evolved, diversified among single-celled forms, but nothing dramatic happened. Why? We're not entirely sure. Perhaps oxygen levels weren't yet high enough to support more complex life. Perhaps the ecological conditions weren't right. Perhaps certain key innovations, like the evolution of sexual reproduction, which dramatically increases genetic diversity and speeds evolution, hadn't yet occurred or hadn't yet become widespread. But around 800 to 600 million years ago, things began to change again. Oxygen levels rose, possibly to near-modern levels. Another series of severe glaciations occurred, more snowball Earth events. And when the planet thawed, life emerged transformed. Multicellular organisms appeared, not just simple colonies of identical cells, but organisms with differentiated cell types, with different cells performing different functions. Organisms that were no longer microscopic, but visible to the naked eye, millimeters or even centimeters in size. These early multicellular organisms are called the Ediacaran biota after the geological period in which they lived. They're strange creatures, unlike anything alive today, flat, quilted things lying on the seafloor, absorbing nutrients. Some looked like ferns, others like pancakes, still others like air mattresses with segments. We're not entirely sure what they were. Some might have been early animals. Others might have been fungi or algae. Some might represent entirely extinct kingdoms of life. They left few clear descendants, and most disappeared before the next great explosion of evolutionary innovation, because what came next would dwarf everything that had come before. Around 540 million years ago, in a geological blink of an eye, animals appeared in stunning diversity. This is the Cambrian explosion, and it would set the stage for all the complex ecosystems we see today. But that's a story for the final part of this chapter. First, let's appreciate how far life had come, from simple bacteria 4 billion years ago to complex eukaryotic cells, from an oxygen-free world to one where oxygen enabled new levels of energy production, from single cells to the first experiments in multicellularity. The stage was set. The actors were in place, and the greatest show on Earth was about to begin. 600 million years ago, Earth was emerging from the last of the great snowball glaciations. Ice sheets retreated, oceans warmed, and in those oceans, something remarkable was happening. Single-celled eukaryotes, which had existed for over 1 billion years, were beginning to stick together, to cooperate, to form bodies composed of many cells working in coordination. Multicellularity isn't as rare as you might think. It's evolved independently dozens of times in different lineages in animals, plants, fungi, algae, and even some bacteria. Clearly, there are advantages to being multicellular, advantages that evolution has discovered repeatedly. What are those advantages? For one, size. A single cell can only grow so large before physics works against it. The surface area to volume ratio becomes unfavorable. There's not enough surface to absorb nutrients and expel waste for the volume of the cell. But a multicellular organism can grow almost indefinitely, adding more cells. Size brings benefits. Larger organisms are harder for predators to eat. They can capture larger prey. They're less vulnerable to environmental fluctuations. A small change in temperature or chemistry might kill a bacterium, but barely affect a larger organism. But multicellularity offers something even more important: division of labor. In a single cell, one cell has to do everything: absorb food, produce energy, maintain structure, reproduce. But in a multicellular organism, different cells can specialize. Some cells can focus on capturing food. Others can specialize in movement. Still, others can form protective layers or reproductive structures. This specialization allows for much greater efficiency and complexity. Think about your own body. You have nerve cells specialized for signaling, muscle cells for movement, digestive cells for breaking down food, immune cells for fighting infection. No single cell could do all of these things well, but working together, they create a functioning organism. The earliest multicellular organisms were probably simple, loose colonies of cells that could separate and live independently. Some modern single-celled organisms do this today. When food is abundant, they live as individuals. When food is scarce, they aggregate into multicellular slugs that can move and find better conditions. But true multicellularity requires more. Cells must remain connected throughout the organism's life. They must communicate and coordinate their activities, and crucially, they must accept that most cells will never reproduce. In your body, only germ cells, eggs or sperm, pass on their genes. All other cells are evolutionary dead ends, existing only to support the reproductive cells. This requires a level of cooperation that seems almost altruistic. Why would cells give up their individual reproduction to support the whole organism? The answer is that in a multicellular organism, all cells are genetically identical, clones of each other. By supporting the reproductive cells, somatic cells are supporting copies of their own genes. It's genetic self-interest, just operating at a higher level of organization. By 600 million years ago, multicellular organisms were becoming common. The Ediacaran biota I mentioned earlier represented a diverse array of multicellular life, though many forms were quite different from modern organisms. They seemed to have lived placidly on the sea floor, possibly absorbing nutrients or filter feeding. But they lacked something crucial. They had no hard parts, no shells or skeletons. This made them vulnerable and also means they left poor fossils. Most Ediacaran organisms are preserved as impressions in sand, giving us only vague outlines of their forms. Then, around 541 million years ago, everything changed. The Cambrian period began, and with it came an explosion of animal diversity unlike anything before or since. In perhaps 20 million years, a geological instant, most of the major animal body plans we see today appeared in the fossil record. This is the Cambrian explosion, one of the most dramatic events in the history of life. Suddenly, the fossil record is full of animals with shells, exoskeletons, and hard body parts. Trilobites, those iconic arthropods with segmented bodies and compound eyes, appeared. So did brachiopods, mollusks, early echinoderms, and bizarre forms like Anomalocaris, a meter-long predator with grasping appendages and compound eyes on stalks. The question that has puzzled scientists for over a century is, why then? Why did complex animals appear so suddenly after billions of years of microbial and simple multicellular life? There's no single answer, but several factors probably combined to create the conditions for the Cambrian explosion. First, oxygen. As I mentioned, atmospheric oxygen had risen to near modern levels by the late Precambrian. Oxygen is crucial for active mobile animals because aerobic metabolism provides the energy needed for muscles, nerves, and other energy-intensive tissues. Low oxygen might have prevented complex animals from evolving earlier. Second, a genetic toolkit. Animals require sophisticated developmental programs to build complex bodies with different cell types arranged in precise patterns. These programs are controlled by regulatory genes, particularly Hox genes, which specify body segments and organ positions. Research suggests that these genetic toolkits had evolved by the early Cambrian, giving evolution the raw material to work with. Third, ecology. The Cambrian explosion may have been driven partly by an evolutionary arms race. The evolution of predators, animals that actively hunt and eat other animals, created selection pressure for defenses: shells, spines, speed, camouflage. Prey evolved better defenses, predators evolved better weapons, and the cycle continued. This feedback loop could have rapidly driven the evolution of complexity. Fourth, environmental change. The end of the snowball Earth glaciations may have created new habitats and ecological opportunities. Ocean chemistry was changing, with calcium becoming more available, useful for building shells and skeletons. Continental configurations were shifting, creating new shallow seas ideal for marine life. And fifth, perhaps most speculatively, vision. Some scientists argue that the evolution of complex eyes, allowing animals to see predators and prey from a distance, fundamentally changed ecology and drove an evolutionary arms race. Suddenly, hiding wasn't enough. You needed armor, speed, or intelligence to survive. Whatever the exact causes, the result was stunning. The Cambrian oceans were full of weird and wonderful creatures. Opabinia, with 5 eyes and a trunk-like grasping organ. Hallucigenia, covered in spines with legs that still confuse paleontologists. Wywaxia, armored with scales and spines. And of course, early relatives of modern animal groups. Primitive fish, early arthropods, mollusks, echinoderms. These weren't just random forms. They represented the establishment of the basic animal body plans we see today. Bilateral symmetry, a body plan with left and right sides that mirror each other. Segmentation, repeating body units that could be modified for different functions. Heads, concentrations of sensory organs and nervous tissue at the front of the animal. And crucially, the evolution of hard parts, shells, skeletons, teeth. These served as armor and weapons, but they also left beautiful fossils, giving us a detailed record of Cambrian life. The Burgess Shale in Canada and Chengjiang in China preserve exquisite fossils, showing not just hard parts, but also soft tissues, eyes, guts, and muscles. What we see in these fossils is the beginning of modern ecosystems, complex food webs with producers, consumers, and decomposers. Predator-prey relationships, competition and cooperation, animals burrowing into sediment, creating new habitats, reefs forming from archaeocyathids, early sponge-like organisms. Life had moved from the simple microbial mats of the Precambrian to complex ecosystems rivaling modern ones in sophistication, if not in species diversity, but the Cambrian was still entirely marine. Life on land remained limited to microbial crusts and perhaps some simple fungi. The continents were barren, rocky landscapes, lifeless except for these microscopic pioneers. That would change in the next great transition, the colonization of land. Plants would venture onto shore, followed by arthropods, then vertebrates. But that colonization required the legacy of the Cambrian, the complex body plans, the genetic toolkits, the ecological relationships that would be adapted for a completely new environment. It also required the oxygen that cyanobacteria had spent billions of years producing. Land animals need to breathe oxygen from the air. The oxygen-rich atmosphere created by photosynthesis made land colonization possible. And it required the evolution of new structures, roots to anchor plants in soil, lungs to breathe air, legs to support body weight against gravity. Each of these innovations built on what had come before, using the genetic and developmental machinery evolved during the Cambrian. By 400 million years ago, plants had colonized land, creating the first forests. Arthropods followed, early insects, spiders and scorpions. Then came tetrapods, four-limbed vertebrates that evolved from lobe-finned fish and gave rise to amphibians, reptiles, and eventually mammals and birds. Each transition opened new opportunities. Forests created new habitats. Herbivores evolved to eat plants. Carnivores evolved to eat herbivores. Flight evolved multiple times independently in insects, pterosaurs, birds, and bats. Complex behaviors emerged: parental care, migration, hibernation, tool use. And throughout this journey, mass extinctions periodically reset the playing field. The Permian extinction, 252 million years ago, wiped out over 90% of species. The Cretaceous extinction, 66 million years ago, caused by an asteroid impact, ended the age of dinosaurs and allowed mammals to diversify. Each time life recovered. New species evolved to fill vacant niches. Ecosystems rebuilt themselves, often in new configurations. Evolution is resilient, relentless, constantly exploring new possibilities. And finally, just a few million years ago, one lineage of apes in Africa began to walk upright, use tools, control fire, develop language, and ask questions about their origins. We are the latest chapter in this 4 billion year story, inheritors of the chemistry, the cellular machinery, the genetic code, and the evolutionary history that connects us to every living thing. When you breathe, you're using oxygen produced by cyanobacteria and plants through photosynthesis, the same innovation that caused the Great Oxidation event. When your cells produce energy, they're using mitochondria, former bacteria that entered into symbiosis billions of years ago. When you grow from a fertilized egg, you're using Hox genes and developmental programs that originated in the Cambrian. You are, quite literally, a product of Earth's 4.5 billion year history. You are made of elements forged in stars. You are animated by chemistry that learned to copy itself in Earth's ancient oceans. You are built on body plans established in the Cambrian seas. You are sustained by an atmosphere transformed by ancient bacteria. This is not metaphor, this is scientific fact. The origin of life on Earth isn't just an interesting story about the distant past. It's your story. It's the story of how the universe organized itself through chemistry and physics and evolution into beings capable of contemplating their own existence. From the violent birth of a planet, to the first self-replicating molecules, to single cells, to complex organisms, to consciousness, it's all one continuous process, unbroken across billions of years. And it's all explained by science, by careful observation and experimentation and reasoning. The origin of life is a mystery we're still solving. We don't have all the answers. We don't know exactly where or when or how the first self-replicating molecules arose. We're still debating the relative importance of different factors in the Cambrian explosion. We're still discovering new pieces of the puzzle, but the broad outlines are clear. Life emerged from chemistry through a gradual process of increasing complexity. It diversified and adapted and transformed the planet. And it continues to evolve, to surprise us, to remind us that we are part of something far larger and older than ourselves. This is the story of life on Earth, as best we understand it today. And it's a story that continues, with us as its newest narrators. 4.5 billion years. It's a span of time so vast that our minds can barely grasp it. If you compressed Earth's entire history into a single 24-hour day, humans would appear in the last few seconds before midnight. Our entire recorded history, all of civilization, all of written language, everything from the pyramids to the internet, would occupy less than the blink of an eye. And yet, here we are, conscious beings made of stardust and ancient chemistry, capable of looking back across that immense gulf of time and piecing together our own origin story. It's extraordinary when you really stop to think about it. We've journeyed together from a cloud of gas and dust to the formation of our planet. We've watched Earth cool from a molten sphere, seen the first oceans condense from the atmosphere, witnessed the late heavy bombardment that nearly sterilized the surface. We've explored the chemistry that built organic molecules from simple gases and minerals. We've considered the environments, hydrothermal vents, tidal pools, mineral surfaces, where those molecules might have organized into the first self-replicating systems. We've traced the transition from chemistry to biology, from molecules to cells, from simple replicators to sophisticated organisms with DNA, proteins, and membranes. We've seen how bacteria conquered the planet, diversifying into countless forms and metabolic strategies. We've witnessed the great oxidation event, that catastrophic transformation when oxygen-producing cyanobacteria fundamentally changed the atmosphere and set the stage for complex life. We've explored the evolution of eukaryotic cells through endosymbiosis, that remarkable event when one cell engulfed another and formed a partnership that would become the basis for all complex life. We've watched multicellular organisms emerge, experimenting with new body plans and new ways of living. And we've stood in awe of the Cambrian explosion, when life seemed to explode in diversity, filling the oceans with strange and wonderful creatures. From there, life spread to land, conquered the air, survived mass extinctions, and continually reinvented itself. Forests grew, dinosaurs rose and fell, mammals diversified. And eventually, apes came down from the trees, started asking questions, and began the long journey toward understanding where they came from. That's the story. That's our story. And it's not mythology, not speculation, but science, the product of centuries of careful observation, experimentation, and reasoning. Yes, there are gaps. Yes, there are mysteries. But the broad outlines are solid, supported by evidence from geology, chemistry, biology, and astronomy. What strikes me most about this story is its continuity. Life didn't start and stop, appear and disappear. Once it began, it continued. Through ice ages and asteroid impacts, through volcanic eruptions and shifting continents, through mass extinctions that wiped out most species, life persisted. It adapted, evolved, found new ways to survive, and not just survive, to thrive, to become more complex, more diverse, more remarkable. From simple bacteria to redwood trees that tower 100 meters high, from single cells to blue whales, the largest animals ever to exist. From mindless chemistry to human consciousness, capable of art and music and mathematics and love. There's something almost defiant about life. The universe tends toward entropy, toward disorder, toward simple uniformity. Yet life pushes in the opposite direction, building complexity, creating order, organizing matter in increasingly sophisticated ways. It's not violating the laws of physics, it's using them, exploiting gradients and energy flows to create temporary islands of order in a sea of entropy. Every living thing on Earth, from the smallest bacterium to the largest whale, is engaged in this same project, maintaining itself, growing, reproducing, passing on information to the next generation. We're all, in a very real sense, doing the same thing that the first self-replicating molecules did 4 billion years ago. We're just doing it with far more sophisticated machinery. And that machinery, your body, your cells, your DNA, carries within it the echoes of that entire 4 billion year journey. The genetic code you use to build proteins is the same code bacteria use, the same code plants use, the same code every living thing uses. It's a frozen accident from the early days of life, preserved because evolution is conservative, because changing something so fundamental would break everything built on top of it. Your mitochondria still resemble the bacteria they once were. Your body still uses metabolic pathways that evolved billions of years ago. Your eyes use light-sensitive proteins related to those in ancient archaea. You are quite literally a living fossil, carrying within you structures and molecules that date back to life's earliest days. But you're not just a fossil. You're also evolution's cutting edge, the latest iteration in an unbroken chain of ancestors stretching back to LUCA, the last universal common ancestor. Every one of your ancestors, without exception, successfully survived long enough to reproduce. That's billions of years of unbroken success, of adaptation and survival against tremendous odds. You are improbable, the specific combination of genes that makes you you, that unique shuffling of DNA from your parents, will never occur again. And yet you are also inevitable. Given Earth's history, given the chemistry of carbon and water, given 4 billion years of evolution, something like you, some conscious, intelligent, curious being, was perhaps bound to appear. Eventually, David Attenborough has spent his life showing us the wonders of the natural world. The dancing birds of paradise, the hunting cheetahs, the ancient forests, the coral reefs. Each one is a marvel of evolution, a solution to the problem of survival, a poem written in DNA. But perhaps the greatest wonder is the story itself. The fact that we can tell this story, that we can trace our origins back through the fossil record and the genetic code and the chemical traces in ancient rocks. The fact that we can stand on this planet and understand, even partially, how we came to be here. Science hasn't diminished the wonder of life. If anything, it's amplified it. Knowing that you're made of atoms forged in dying stars doesn't make you less special. It makes you part of the cosmos in the most literal sense. Knowing that you share ancestors with every other living thing doesn't diminish your uniqueness. It connects you to an unbroken chain of life stretching back to Earth's earliest days. And knowing that life emerged from chemistry, that consciousness arose from matter, that meaning and purpose can exist in a universe governed by physical laws that might be the most profound realization of all. We are the universe becoming conscious of itself, matter organized in such a way that it can ponder its own existence. There are still mysteries, of course. We don't know exactly where life began. We haven't yet created life from scratch in a laboratory. We don't fully understand consciousness or how it emerges from neural activity. We're still discovering new species, new ecosystems, new aspects of biology we never imagined. But that's part of the beauty of science. It's not a fixed set of dogmas, but an ongoing exploration, a conversation with nature that's been proceeding for centuries and will continue for centuries more. Every answer raises new questions. Every discovery opens new avenues of inquiry, and you can be part of that exploration. You don't need a laboratory or a PhD. You just need curiosity. That same curiosity that drove our ancestors to wonder about the stars, that drove Darwin to puzzle over finches, that drives scientists today to peer at ancient rocks and Sequence genomes and build complex models of Earth's early atmosphere. Look at a tree and realize it's capturing sunlight using molecular machinery inherited from ancient cyanobacteria. Look at your hand and realize it's built using developmental programs established in the Cambrian seas. Look at the night sky and realize the atoms in your body were forged in stars that died before the sun was born. These aren't abstract facts. They're deeply personal truths about who you are and where you come from. You are part of this story, this vast epic, still unfolding story of life on Earth. And the story continues. Life is still evolving, still adapting, still exploring new possibilities. New species are emerging even as others go extinct. Ecosystems are changing, sometimes because of natural processes, increasingly because of human influence. We've become a geological force, capable of reshaping the planet as profoundly as those ancient cyanobacteria that first poisoned the atmosphere with oxygen. What happens next is, in part, up to us. Will we be wise stewards of the living world we've inherited? Will we preserve the diversity of life that 4 billion years of evolution has created? Will we venture into space, perhaps seeding life on other worlds, continuing the great experiment that began in Earth's ancient oceans? These are open questions. The story isn't finished. In a very real sense, we're now among its authors, shaping Earth's future through our choices and actions. But whatever the future holds, the past is clear. We know where we came from. We know how the impossible became possible, how chemistry became biology, how single cells became complex organisms, how consciousness emerged from matter. We know our place in the great tree of life, our connection to every other living thing. And we know that we're not separate from nature, not observers looking in from outside, but participants, products of the same evolutionary processes that shaped everything else. We're nature becoming conscious of itself, life pondering its own origin. That's a profound responsibility, but it's also a tremendous privilege. To be alive, to be conscious, to be capable of understanding these things, it's an astonishing gift, the product of billions of years of cosmic and biological evolution. So the next time you breathe, remember that you're inhaling oxygen produced by photosynthetic organisms, continuing a process that began billions of years ago. The next time you eat, remember that you're participating in energy cycles that connect you to the sun and to every other living thing. The next time you wonder about something, remember that curiosity itself is an evolved trait, something natural selection favored, because understanding the world confers survival advantages. You are a child of the cosmos, a product of Earth's history, a temporary arrangement of atoms that will eventually dissolve back into the world from which they came. But for now, for this brief moment in cosmic time, you exist. You're alive, you're conscious, you're capable of wonder, and that perhaps is the greatest miracle of all. Not that life began, but that it continues. Not that we exist, but that we can know we exist, can understand our origins, can tell this story and marvel at its beauty. From stardust to consciousness, from chemistry to curiosity, from molecules to meaning, that's the origin of life on Earth. That's your origin, that's our shared inheritance and our common future. And it's absolutely, undeniably, wonderfully extraordinary. If this journey through deep time has stirred something in you, curiosity, wonder, or perhaps a deeper appreciation for the living world, then I encourage you to keep exploring. Read about evolution, about geology, about chemistry and astronomy. Visit natural history museums, watch documentaries. Look at the living things around you with fresh eyes, seeing them not as static objects, but as fellow travelers in this great evolutionary journey. Share this story with others. Talk about where we came from, how we're connected to everything that lives. In an age when science is sometimes viewed with suspicion, when our relationship with the natural world is increasingly strained, we need to remember these fundamental truths about who we are and where we come from. And if you found value in this exploration, if this story has changed how you see yourself and the world, consider subscribing to this channel. There are more stories to tell, more wonders to explore, more connections to make between the scientific facts and the deeper meaning they reveal. Because understanding our origins isn't just an academic exercise. It's a way of understanding ourselves, our place in the universe, and our responsibility to the future. We are, all of us, participants in an ongoing story that began billions of years ago and will continue long after we're gone. What role will we play? What legacy will we leave? Those are questions worth pondering as we stand here, improbable conscious beings on a small planet, looking back across the vast expanse of time to understand how we came to be. Thank you for joining me on this journey. Until next time, keep wondering, keep questioning, and keep marveling at the extraordinary reality we're privileged to inhabit.